Friends, in our last recorded lessons for Chapter 1, I want to do some wrap-up. I want to talk a little bit about the resonance theory and how important it is to be able to draw electron push arrows correctly. So in the last few sections, let's begin our lessons looking at the resonance theory. There's in many molecules and some ions, polyatomic ions, especially those that contain pi bonds. Remember, that's just code for saying double or triple bonds. More than one equivalent Lewis structure can be drawn to represent the same structure. We look at a polyatomic ion, for example, called carbonate. CO3 2 negative is the polyatomic ion called carbonate. Carbon is the central atom, and we've attached back the three oxygens in the polyatomic ion. One of the oxygens ended with a double bond. Two of the other oxygens landed with a single bond. And notice that we see the negative sign on each of the oxygens left and right here on the bottom. Just to remind ourselves, those are the charges developed from formal charge. To remind us, oxygen lives in group 6, but this oxygen has 7 assigned electrons, making it a -1 overall. And the same is true over here. This negative sign is truly representing the formal charge of -1. And so what we're looking at there is, and when I draw this in class, I tend to put polyatomic ions inside of a bracket and place the charge outside. The formal charge of this polyatomic ion does indeed match the charge given to carbonate as 2 negative. But back to the term resonance structure, what we're looking at is an opportunity to draw the double bond to either of the 3 oxygens and have them all represent equivalent structures. Not that you're just moving the double bond by spinning the molecule, but you're actually attaching it to a different oxygen atom. So not spatial change, but breaking bonds and forming new bonds. And to highlight that, I'm going to remind us that if the double bond from carbon to oxygen number 1 is very different than an oxygen double bond to carbon number 2, you're literally taking this bond and moving it to a different oxygen atom. Not just a simple rotation of the molecule, but a bond breaking and a new bond forming. The term resonance develops when you have more than one correct answer. Where can I place the double bond? Do I have to go to carbon 1 or 2 or 3? And the answer is it's correct in any direction. And truly, the better answer is it's in all directions, isn't it? A resonance structure is not truly a single bond or a double bond, but kind of that tweener bond between the length of a single and a double. It says structures 1 through 3, although not identical on paper, are equivalent. All of its carbon-oxygen bonds are of equal length. Now I want to remind us in terms of bond length. The longest bond length is a single bond. A little bit shorter is a double bond, and even shorter would be a triple bond. That's the bond length. The greater the electron density between the 2 atoms, the tighter the pull, the bonds become shorter and shorter as you increase the bond to double to triple. This resonance structure is of the length between a single and a double. It's not quite a single, it's not quite a double. The term is called delocalized. That bond exists evenly between the central atom carbon and all 3 of the oxygens at any given moment. Sometimes you see a resonance structure drawn to remind you that it's of equal length by using a dashed line instead of the solid line that you might see for a true covalent bond. Equal bond length tells us that it is delocalized. To delocalize the bond says this shared pair of electrons is spending equal amount of times between oxygen number 1, oxygen number 2, and oxygen number 3. So this bond is not of a single bond length. It's not a double bond length. In all directions, standing at the carbon and look in all directions, those oxygens are equal distance in all directions. Now, the delocalized pi bond creates a resonance structure where the bonds are of equal length. Now let's talk about what we're seeing here with these arrows. Curved arrows are used to show the movement of both bonding and unshared electrons. So bonding and unshared electrons, that's what this is referring to. These arrows are showing the movement of these electrons as one resonance structure converts into the next. A double barbed arrow shows the movement of a pair of electrons, a double barbed arrow. And later on, in a next chapter coming up, not even real soon, but in a next chapter, we look at a single barbed arrow as the motion of just one electron when we're talking about a radical or charged ion. So in this chapter, we will always have a double-headed arrow. A curved arrow should originate at the location of the electron in the initial formula and point precisely to where those electrons will be drawn in the new formula. So the origin starts at the bond or the electron pair that's moving, and it's going to point where the new electrons were placed. Let me emphasize that again, kind of clean the slate here. In this double bond, this is a pi bond. It's the second in a double bond. So this is the delocalized pi bond. I originate the arrow at the bond itself, and I click and drag those electrons to the site where you now see them. Notice how this had 2 pairs of electrons, and now this has 3 pairs of electrons, and the double bond is gone. I moved the double bond, and it became an electron set on the other oxygen. This negative charge is referring to a pair of electrons. I originated the pair of electrons and moved those electrons to the bond. Notice how this now develops a double bond. I took a pair of electrons and made a double bond. You'll get marked wrong if you accidentally release on the carbon or you accidentally release back on the oxygen. You must be very specific where you release the arrowhead. As I move from structure 2 to 3, what's changed from structure 2 to 3? Well, in this direction we had a double bond. Over here we don't. So I'm going to move a pi bond, the delocalized bond, back to the atom of oxygen. It now has those 6 electrons with the -1 formal charge. But I notice now there is a double bond in a position there wasn't before. So I'm capturing this set of electrons. So I originate my arrow at that set of electrons and release it on the bond. And that forms that second bond, the pi bond in the double bond. Just take some practice, especially in sapling, of clicking and dragging the arrowhead to make sure you release it in the correct place. Now notice here, this is the hydroxide polyatomic ion. What's not shown are the valence electrons on the oxygen. We can show them there so we can see them. So the OH, let me just hit the pen, the OH, -1. So I have to start the arrow at the origin of the electrons I'm moving. I'm going to move a pair of electrons, so I start the arrow at the origin of the electron, and I move it to the place that is going to accept the electron. When I move that, I'm showing the negative being attracted to the positive. It is incorrect to originate an arrow at an electron deficient site. I'm going to repeat that. It is incorrect to originate an arrow at an electron deficient site. H positive has no electrons, so therefore I cannot begin an arrow there and point towards the electron. Negative, because this is an electron push arrow. We're tracking electrons. Here's a lone pair of electrons on the nitrogen. This is the molecule ammonia. In this particular region, we have a polar functional group. We're going to learn in the next chapter, this is called the carbonyl functional group, a C double bond O. Now remember, this oxygen has a lone set of electron pairs to finish its octet. This exposed electron area on top of the oxygen makes it a partial negative charge. Because the electron distribution is being pulled from the carbon out onto the top of the molecule and the top of the oxygen, that uneven electron distribution makes the molecule polar. That leaves the carbon slightly positive. This pair of electrons, remember the arrow originates at the electrons that we're moving, and it will point to the positive region that you're attaching to. You would never see a positive carbonyl moving its electrons. This is electron deficient. You originate the arrow where you see electron-rich areas. And again, when we see an electron-rich area, it will point to the positive. We might have a second shift that moves an electron dot. Remember, if you're moving a bond, it ends up as two dots. If you're moving electrons over here, it'll end up as a charged particle. So electron push arrows. Now, resonance structures then are just not real structures, and they exist truly on paper. It's a hybrid of all three of them at once. It's not like the molecule exists like this for a moment at a time. It's not like it exists as this for a moment at a time, and it's not this at any moment in time. It's a hybrid of all of them at once. That's why we see sometimes, to get a better visual, we're saying, okay, that's truly what it is. It's a delocalized bond at any one time between the carbon and all three of the oxygens. Also note that we have a double-headed arrow that separates the resonance structures. It is incorrect to have two arrows pointing in opposite directions. That represents equilibrium. Remember equilibrium, where A and B can go on to make products C and D, and at the same time there's a competing reaction of the reverse direction. That's what's called equilibrium. That's incorrect. We want resonance structures with a double-headed arrow, meaning that it's back and forth between the two. Getting rid of my phone. That's the dinging you're hearing. Rule 2. We are only allowed to move electrons in writing resonance structures. So that means I can move electrons, but never, ever am I allowed to move atoms. So these are resonance structures. CH3, same. CH, the same. CH, the same. CH2, the same. What's changed is the electron distribution between the carbon backbone of the compound. That's okay. You can change the electron distribution to create resonance structures. Doesn't necessarily mean they're all created equal in terms of energy content, but they are all valid structures. It's not proper to move an atom. So notice right off, I have a violation right here. I moved a hydrogen to somewhere else. I moved it, which was here, to now here. I can't have H3C and a CH just all of a sudden turn to H2C and added the H over here. That's not allowed. Only electrons can move, not the atom. And all of the Lewis structures must be proper. I mean, it can't break an octet rule. Like, it wouldn't make sense to have carbon with 5 bonds. That's an improper Lewis dot structure for carbon, and therefore it is not an acceptable resonance structure. Carbon would never have 5 bonds. That's rule 3 in drawing a resonance structure. The next guideline, the energy of the resonant hybrid is lower than the energy of any contributing structure. So again, the hybrid of all of the separate little pictures, the truth is that it's a blend of all three. And that resonance structure truly stabilizes the molecule. It makes it a very stable, low-energy compound. And it's especially true when the resonance structures are equivalent. just like the carbonate ion, when we simply move a double bond that is equal in any direction, that's truly a stabilizing element to that structure. If the resonance structures are equivalent and the resonance then stabilization is very large. The more stable a structure is, the greater its contribution to the overall hybrid structure. What are those things that make a resonance structure more stable? Well, the more covalent bonds a structure has, the more stable it is. Well, let's kind of look at that. Here's 1, 2, 3, 4 covalent bonds on this particular carbon. Here's 1, 2, 3 bonds on that central carbon. Which one is a more stable resonance structure? The one with more covalent bonds is the more stable structure. Number 2 says charge separation decreases stability. So if I have a carbon chain and I have for whatever reason, a positive cation on this carbon and a negative carbanion here, for whatever reason, we're having a reaction occur, they're right next door to each other. Whereas if I have a 4-carbon chain and I have a positive separated by a great distance to the negative to balance that charge, that's less stable. That the charges should be next to each other to help stabilize the compound. And number 3, structures in which all atoms have a complete valence shell, in other words, they're all following the octet rule, will trump the day. That's a very stable configuration. Like with this carbon here, it does not have a complete octet. Therefore, it is less stable than a carbon who does have a complete octet. This one I did a screenshot. It's off of an old test. And we'll kind of look at a test question so you can see it's a multiple choice format. Identify the major and minor resonance contributors for the azide ion. Azide is N3, and it has a -1 charge overall. One of the strategies with a multiple choice question, and quickly you can eliminate some of these choices just with some quick math. For example, nitrogen lives in group 5, so each nitrogen is going to contribute 5 electrons, so that's 15. The -1 charge says you have an extra electron, so I have to have 16 dots. Some of these structures may not have 16 electrons. For example, and I want to make that pen thin so I can write smaller. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Letter D, when I count the shared pair in a bond is 2 electrons, and each lone pair, of course, is 2 electrons. I count 18 electrons on structure D. Well, that helps me eliminate letter D quite readily because it has an incorrect number of dots. Also, I want to make sure that, considering formal charge, you want to alleviate formal charge best you can on each of the elements. Look at here, we have a plus 1 and a -2. That's a big magnitude of a formal charge. I think letter A and B, just based on seeing a formal charge of 2 negatives, it's too big. I think with confidence I can eliminate based on formal charge, structure A and B. Now here's what I like with C and E. I haven't checked much else yet, but I like the magnitude of the formal charge. Plus, you know what I'm noticing right off here? -1 plus 1 is 0, and I'm back to -1. So adding the formal charge matches the charge on the ion for letter C, plus 1 plus 1 and a negative. This structure gives me a formal charge overall plus 1. And that's not the formal charge we're looking for. The charge on the ion is -1. So that makes no sense for letter E. You see how it's strategizing? Check for the correct overall charge. I could eliminate some of those. Which one has the most covalent bonds? That got rid of letter D as well. Minimize formal charge. Which one are you thinking is the best structure for the resonance of a zide, N3 negative? We said structure D and E were not accurate. Too many electrons. A net charge of -3 or a net charge of +1 helped us eliminate some of those. The major contributor to a resonance has the greater number of covalent bonds, has any negative charges on the most electronegative element. Well, they were all nitrogens in this case, so that really didn't help. But they minimized the formal charge on each atom. So we said the major contributor, based on many factors, was structure C. And we agreed with that. And I kind of talked through the logic of how we could eliminate some quite readily. That's the skill level we're looking to obtain with the term resonance. What is the most stable configuration based on a series of questions? Now here's a sapling. Draw a major resonance structure for the following. And enolate is the name. Use curve arrows. So when you click on your sapling, you'll have one of these toolbars that come up and a curved arrow. Make sure it's a double barbed arrow to show the delocalization of the electron pairs in both the forward and the reverse direction. So we have to turn this structure, I'll call structure 1, into structure 2. And then on this side, we have to draw arrows that turns it back into the original structure. Make sure that you include lone pairs and formal charges. And it does tell us to draw these hydrogen atoms, as much so as they've done here. So where do we see an electron-rich area? I see an electron-rich area where I have the negative on this carbon right here. The negative sign makes this the electron-rich arrow. So I'm going to originate my arrow to push those electrons to create a double bond between carbon and those two hydrogens. The negative sign is no longer there because we removed the formal charge. This group, CH3, remained the same. There is no electron-rich arrow here. There's nothing unusual. But I do see an opportunity then to continue shifting the electrons. We have to develop a negative charge somewhere. Remember, the molecule must retain the same overall charge, which was -1. So I'm going to take that, what used to be the double bond, take those pairs of electrons that are forming a bond and make them lone pairs. And there's my formal charge now on the oxygen as a -1. So in structure 1, I had 2 electron arrows that were necessary to create the new structure we drew. And then, of course, on this, I have to just go back and replace those arrows that turn it back into the original structure. And that's the skill there that's going to take a little practice with clicking and dragging the arrows. So we saw the first arrow brings a lone pair to create a double bond. The double bond breaks and forms another set of lone pairs on the electron, and just undo what you did to form the new structure. Draw the other significant resonance contributor for the following compound. Include lone pairs of electrons, formal charges, and hydrogen atoms. Here's a CH3, and look at those electrons up here, double bond C, double bond O, and I can see double sets of electrons. What do you think we should do to create a resonance structure, knowing we can only move electrons and not atoms? Any ideas? Let you think a little bit. When you see the electron-rich arrow, how do you know, just think about that with me. How do we know to go in this direction instead of this direction? Well, if I did this direction to the left, I'm going to all of a sudden create an invalid number of electrons on this terminal carbon. It already has an octet. I recommend don't mess with it. Alrighty, it has the 3 hydrogens on there. If I brought a double bond, it would create a hypervalent carbon. Alrighty, so that's how I'm getting the idea that I can move it this way. Alrighty, now when we do that, what else do we need to shift? Well, this carbon cannot end up with 5 bonds either, so I need to break another bond and move a pair of electrons. And see, that's exactly what you've done. Instead of having a double bond here, you create a set of electron pair on the final oxygen, and notice now we have a formal charge being shown of -1. Moving the lone pair of electrons to make a triple bond left the nitrogen with the formal charge of +1. It's still 0 overall, but I now have formal charges. You can clearly see the major contributor would be this based on formal charge, but this is a valid resonance structure. Remember formal charge, nitrogen lives in group 5. It has 1, 2, 3, 4 assigned electrons, a +1 formal charge. Oxygen lives in group 6, draw a circle, 1, 2, 3, 4, 5, 6, 7 assigned electrons, a -1 formal charge. So just reminding us why they have positives and negatives now in the structure. Our remaining lessons will kind of review the Vesper chart, which I did when we did our Lewis dot structure, sigma and pi bonds and bond angles. I feel I did a pretty good job with that when we did our previous lessons. I didn't want to say it was sections 4 and 5 when we kept drawing Lewis dot structures. I would toss in sigma pi bonding, bond angles, and the Vesper chart. So I'm going to say the rest of this is kind of a review session from things that I sprinkled in earlier notes. Remember, sp3 hybridized is always 4 electron domains. 1, 2, 3, 4. The methyl group is sp3 hybridized, and the bond angles are 109 degrees. They're not 90 degrees like they're showing here. Methane is sp3. We talked about putting in a double bond, and that becomes sp2 hybridized. We called that trigonal planar. I can spell trigonal planar. And here's a nice visual of all of those falling onto the same plane. The double bond creates a pi orbital, creates rigidity in the molecule. Remember, sigma bonds have total freedom to rotate. However, pi bonds create a rigid structure that can no longer rotate. sp2 hybridized introduces that concept of cis and trans in terms of structural isomers. Remember the terms cis and trans from previous lessons. If you have cis-trans chemistry, you're looking at an arrangement where on one side up, the other side down from a double bond was called trans, and if they're on the same side, they're called cis. And we should sure practice that, especially when we start building molecules. Here we have trans configuration on the double bond. The first carbon has the chlorine pointing up. The second carbon has its bromine pointing down, a trans position. Same molecule, but the double bond now has them pointing in the same direction, cis. They have very different physical properties in terms of boiling points, melting points. So the molecular geometry really does matter, and that's why it's stressed when we talk about, in terms of molecular geometry. We need to know that to predict how a molecule will react with a specific reagent. Here's a double bond. We have hydrogen, hydrogen, opposite sides. Or you can think of the ethyl group. On opposite is trans, same side, cis, and so forth. Become familiar with this cis-trans configuration. And I know this is a snapshot from your sapling that talked about cis-trans, and can this molecule actually exhibit cis-trans. And first of all, we need a double bond. So I see a double bond between carbon 2 and carbon 3. One of those positions is a hydrogen, and the other is a methyl. And what have I just drawn here for that structure? That's the cis conformation. Because I could have also drawn a trans conformation by placing opposite. I'm getting there. There's the trans. This has a double bond, the carbon-carbon double bond. I have one side is a methyl group, and the other side is a hydrogen. See, this hydrogen is attached to the carbon, that's this one, and then the methyl is attached to that carbon in the double bond. This carbon has a bromine and an ethyl group. We could have easily switched the bromine and the ethyl group the opposite direction to create the opposite stereoisomer. Here's the double bond. Why doesn't this exhibit cis-trans? Well, look at this. This has an ethyl group on that particular carbon. This is an ethyl group on the other direction. Because they're identical, I will not build anything new by switching these two carbons with these two carbons. That's not a new substance. It's the same darn thing. So because they have identical groups on this carbon, no cis-trans. And here we see a double bond. This looks like the cis configuration. I could have easily drawn the trans configuration and had stereoisomers. Cis and trans practice. And you'll continue through the rest of the lesson here just looking at molecular geometry, what I sprinkled into previous lessons. We have a linear sp configuration with a triple bond. We'll learn that these are called alkynes, Y-N-E, alkyne. If we have a double bond, we know that's sp2 hybridization, and we know that that's trigonal planar, 120 degrees. And here we have all four bonds, so that's sp3 hybridized, and that's tetrahedral with 109.5 degrees. That's truly the end of the lessons. I showed this slide a little bit earlier, the VSEPR chart by electron domains. We're able to figure out, based on the number of domains, how many bonded and unbonded pairs we have to determine the molecular geometry. What's nice in Chapter 2 is we get to review this a little more as we talk about functional groups, polarity of the bonds, polarity of the molecule, and so forth. So if you're not yet comfortable with this, spend some time becoming familiar with what I refer to as your VSEPR chart. It is indeed a test-taking tool page. Look to see right here, this carbon is being asked for. How many electron domains do you see? I count 2 domains. Remember, a domain is any bond. I don't care if it is a single, double, or triple, any bond counts as one domain. An electron pair counts as a domain. So if I'm counting electrons or other atoms, that counts as a domain. So here's 1, 2 domains. Even though it's a triple bond, it's still 2 domains. That means it's sp hybridized, 2 domains. Go back to your VSEPR chart. 2 domains is a linear molecule with 180 degrees. This is going to be the same answer, isn't it? This carbon has exactly 2 domains. It's a linear structure, sp hybridized. Here's a carbon, 1, 2, and remember these hydrogens are actually bonded onto that carbon as well, so that's 4 domains. 4 domains is sp3 hybridized. 4 domains is tetrahedral. That's 109.5 degrees. This carbon has 1, 2, 3, 4 domains. That hydrogen is bonded to the carbon, even though we don't see it necessarily, it's bonded. 4 domains, sp3 hybridized. Carbon's bonded to hydrogen, there's 1 domain. Carbon bonded to the other carbon, 2 domains, and a double bond still represents 1 domain. 3 domains is sp2 hybridized, trigonal planar. Therefore, we know it's 120 degrees, and so forth. This really is the same exact practice reading your VSEPR chart. Tell me what type of what type of molecular geometry, I just gave the answer, for this particular carbon. Double bond is 1 domain attached to 2 other hydrogens. That's 3 domains total, so it's sp2 hybridized. 3 domains is trigonal planar. And you keep practicing through those. I don't want to give all the answers away. sp hybridized, you're looking for 2 domains. Maybe we don't use it. sp2 hybridized, you're looking for 3 domains. sp3, you're looking for 4 domains. This carbon is attached to 3 hydrogens in a single bond to each of the H's. That's 3 domains. Plus 1 more gives it a 4th domain, sp3 hybridized. 1, 2, 3 domains, sp2 hybridized. And so forth. I think I've done really a nice job, and at least I think, kind of talking through the hybridization, the sigma pi bonding, more coming on polarity, so I sprinkled a little bit, but that's coming more in Chapter 2 as well. And this will end our practice session in Chapter 1.